All right. Hi, welcome to the Math 114 review video, or to welcome everybody that's here live, but I already said that because I just hit the record button. I was going to be smarter than that. Ah, well. For posterity, this is the exam 2 review in the spring of 2024. Uh, just in case you're watching this, not during that semester, I might go over some information that's specific to the spring of 2024 for exam number 2. Again, this is Math 234, multivariable calculus, and let's get started. So if you're looking for my review, I should be hosting it in my notes. So in my OneNote program, you can see over on the left side of the screen there where this thing is located. Exam review tabs, this is exam review number 2. So yeah, it's there. And let's do some math. All right. So question number 1. We've got some function. It's a multivariable function, meaning it's got both x and y that get plugged into it. And we want to figure out what the domain of this function looks like. Based on, we're going to sketch some diagram of it. And the problem was kind enough to provide us with a few to choose from. So let's do that. We're going to take the natural log of some mess. So let's start by highlighting what that mess is. It is 4 minus 4x squared minus y squared. And because I'm taking the natural log of that thing, I need to be aware of what kind of things I'm allowed to plug into a natural log. So if we think back to our algebra days, I know that I am only allowed to take logs of positive numbers, meaning that anything that gets plugged into that natural log must be greater than 0. So I'm going to solve that inequality to figure out what my domain should look like. And I'll put it in a form where I can more easily recognize the equation. Probably something like 4x squared plus y squared is less than 4. And that looks like the equation of an ellipse or a circle. Specifically, it's an ellipse because the coefficients on x and y are not the same. So this thing's an ellipse. And we want to be less than 4, which means we're taking the interior of some ellipse. Specifically, this ellipse over here, option C. That's the one we're after. Now, to just discuss the differences between the other options that are here, the one directly above that, A, this looks like 4x squared plus y squared being greater than 4. That's everything on the outside of the ellipse. And B, which is quite similar to C, would be 4x squared plus y squared is less than or equal to 4. That dark blue line around the edge means that we're including the boundary. And we don't want to include the boundary here because we are not allowed to take the log of 0. So we wanted to stick with C, just the part that's the interior of our ellipse and not including its boundary. So past that, what else do we want to do? We'd probably like to identify the level curves of this thing. So what are they going to look like? Well, that's where it probably is going to be helpful to just rearrange what our equation is. So I made some notes over here for myself. What do I think I want to do? Maybe it'll help to start by looking at, oh, that's what I did. I skipped over a question, didn't I? Before we get to the level curves, we should figure out the range of this function. It would help if I could read. So yeah, let's find the range. So I'm just gonna parameterize my equation or my function real quick because it'll be easier to think of it in a slightly different light. I would just want to think of my function as the natural log of t. And no, that's not quite true. I'm not parameterizing my function. I just want to think about the natural log of t. I'm off to a great start today. That's what I get for holding a review on the first day back from break. Needed a minute to get my brain warmed back up. But all right, if we think about just the natural log of t as a function, its range is all real numbers. Right, so as long as the interior of that thing, as long as the input to that function is some positive number, and I can plug in any positive t value that I'd like into the function, the range of it should be all real numbers. So I want to adapt the range of just natural log of t to the function that we have. If I think about the way that the natural log works, the closer that t is to 0, the more negative the log is going to get. Meaning for this function that we have, I just scroll back up a little bit to put it on screen, natural log of 4 minus 4x squared minus y squared. The closer I get to the edge of my ellipse, the more negative that function's going to be. The more negative the natural log will be, because I'm taking the log of something that's very close to 0. Alternatively, to get large numbers out of my natural log, I just want to take the log of a large number. So said all of that to argue that this function won't have a minimum value, so I can get as close to 0 on the inside as I'd like, but it will have a maximum value. So if I look at the maximum of 4 minus 4x squared minus y squared, it has a maximum value of 4. Since that maximum is going to occur at the origin. If both x and y are 0, I get to a maximum value of 4. I'm subtracting an x squared and I'm subtracting y squared. So best I can do is 4 here, meaning that the range of the function I'm interested in, the range of f of xy, is negative infinity to the natural log of 4 with a bracket on that end. Right, the biggest number I'm able to plug into the inside of my natural log is 4. So my maximum y value, or my maximum z value, my maximum function value is natural log of 4. There we go. That's our range. Then on the other side, the next part of the question that we wanted to answer was figure out what the level curves of this thing looks like. What the level curves look like. And slide that over a little bit. Self enough space to work here. So if I want to find the level curves, I just want to take this equation and set it equal to a constant number. Usually we call that thing k. So z or f is some constant number, and just look at the resulting equation. The natural log of 4 minus 4x squared minus y squared. All right, and let's just put this equation into a form that we can recognize. So maybe I'll start by doing e to the k on the left is equal to 4 minus 4x squared minus y squared. And similarly to how I solved the domain, I'll put 4x squared plus y squared on one side, grouping the other stuff on the right. So I get that 4x squared plus y squared is equal to 4 minus e to the k, where k is a constant number, and it's whatever the z value would come out to, since it's like z equals f of xy. But since k is just a constant number, 4 minus e to the k is still a constant number. So even though it kind of looks ugly to begin with, this is really just 4x squared plus y squared equals some constant number, maybe more different k, which is the equation of an ellipse. So even though it's got that exponential part to it, the exponential part is in the constant value for these level curves. So the exponential part doesn't really impact what a single level curve looks like. The shape of each of these level curves are ellipses. And we know that from right here. Let's highlight the parts that I know that's coming from. So to add a few other notes to this style of problem, there are 3 types of domains that we're really paying attention to right now. So let's maybe start there. If I'm looking for a domain, things I'm not allowed to do, I shouldn't divide by 0. Don't divide by 0. Number 2, I don't want to take the square root. Don't take the square root. And by square root, I really just mean in any even root. So don't take the square root of a negative. And third, don't take the log of a non-positive. Don't take the log of a non-positive. Those are the 3 main rules we have for domains right now. Dividing by 0 is bad. Square roots of negatives are bad. Logs of negatives and 0 are bad. So if I've got to find the domain of a function, these would be the first 3 things I'd focus on. Just look within my equation for one of these rules and base my domain on that. And if I'm not doing any one of those 3 things, well, then probably my domain's just all real numbers. But chances are, if we're asking this question on an exam, the answer's not going to be all real numbers. It's going to be something you can actually do some work on, just if I had to guess. All right, some other shapes that we might want to identify as far as what level curves might look like. Let me actually just focus here for a minute so I can see my different styles and different answers on the same screen. So we just had an example where we saw that our level curves were ellipses because we had 4x squared plus y squared equals some constant value. But if we had circles, it would look basically the same, just that the coefficient on x squared and y squared would both be 1. If they have different coefficients, it's an ellipse instead. So it's probably the other 3 that are more interesting to look at. And we'll break down their equations kind of as follows. Lines are going to look like y equals mx plus b. So y equals x plus k, maybe something like that. Where again, the k values that I'll show up here are it's just that constant z value for the level curves. A parabolic shape is one that'll have the form y equals x squared or x equals y squared. We go either way because the variable choice is arbitrary. And then there'll be like some plus k that floats somewhere. And then the hyperbolic shapes might come in 3 different flavors. We might see a y equals 1 over x plus k, or we might see a y equals k over x. Both of those could be a hyperbolic shape, as well as the x squared minus y squared equals k term, or x squared minus y squared expression. There we go. So all 3 of those are classified as hyperbolas, and they have the characteristic there are non-linear terms involving x and y, and they're combined in some way. Cool. So those are the 3 basic shapes that we'll want to narrow down to, or 4 really, because we're also including the ellipses: lines, parabolas, hyperbolas, and circles or ellipses. ellipses. Ellipses are the 3 dots. I'm having a day. To just give an example of what some other level curves might look like, without solving all of them as we go, and just providing a bunch of work that I wanted to then talk about. Here are a few other examples I thought might be worth looking at. So I've got x plus 1 over 3x plus y, trying to figure out what the level curves of that thing look like. And again, I just want to set it equal to a constant number and then put the rest of the equation in terms of something I recognize. So I'm going to multiply my denominator over to the left, was the first step I did. That's, this step right here. Multiplied the denominator over. And then I had linear terms for x and y, so I decided I'd just solve for y, put everything over on the right. So this thing ends up looking like a line, even though at the beginning it probably didn't look that way at all. But the level curves are lines in the end. I have some constant coefficient on x plus some other constant value, even though that, again, because that k is a constant, I get lines. Another one that doesn't initially look like lines, but works out to be that way anyway, is the function x plus y quantity squared. I'll, again, try to put this thing in a form that I recognize. So I set it equal to k. I could take a square root of both sides, and I get that x plus y is equal to plus or minus the square root of k. But again, it's just equal to some constant number over on the other side. And I can rearrange that to look like y equals negative x plus some constant, which again is a line, even though the starting function didn't really look linear at all. The level curves can still come out looking like lines. And for another one, because apparently there are a bunch of these that looked like lines, e to the negative x minus y. It's almost like the one that we started with, but with an exponential instead of a logarithm. But same thing. I want to get x and y out of that exponent, get it down so that I can just have them by themselves. And I end up with negative x minus y is equal to the natural log of k. But again, I'm not really thinking about it as natural log k. I'm thinking of it as some constant. Negative x minus y equals a constant number. And that I can arrange to look like a line. And to finally give ourselves an example that doesn't come out linear, how about just x times y plus 3? I want to just, I suppose, solve this thing for y. So set it equal to k. I can subtract 3 over to the other side, divide by x. I get y equals a constant. It's k minus 3 right now, but the specific numbers don't matter. I'm just thinking of it as a constant over x. And that's a hyperbolic shape. Cool. So that's about as exhaustive as I could be on that first problem. Let's go on to question 2. Yep, we budgeted enough time for the review, I'm sure. So this next problem, what have we got? Looks like we're gonna find a linearization of something. So we want a linearization of some function f. We'll figure out what the linearization looks like as a function, and then turn that into an approximate value, an approximate function value at a point very close to our center. So if I break down the linearization formula as it's listed below, the way I think of these things is that it's got some center value, which is just the function evaluated at our point 3, 0. It's got an x slope, which is related to the x partial derivative, and it's got a y slope, which is related to the y partial derivative. And those are the 3 elements that make up our linearization. So the center value is going to be the exact value of the function at whatever our center point is, And then the x slope and the y slope terms are both just for a small change in x, it's going to be close to just a linear move in that direction. For a small change in y, the value is going to be close to a linear move in the y direction. So that's what our linearization formula kind of, at least to my mind, that's what it looks like. And what else did I want to say here? I had something smart a moment ago. Oh, right. A linearization is really just a tangent plane. That's the smart thing I wanted to say. So linearizations and tangent planes are going to be the same thing. Just one has slightly different labels on it, being the linearization has slightly different labels from the tangent plane, but they mean effectively the same thing. So let's solve some stuff. Let's keep our equation on the screen. Here we go, right there at the top. And I'm going to need the function value. Let me grab that real quick. I need f of 3, 0. So figure out what I get if I plug that into the function. And I am going to get the square root of 3 plus e to the 0 is 1 minus 3. That is the square root of 4, which is 2. And 2 minus 3 is -1. If I can be trusted to do some of that simple math. Pretty sure that's what it comes out to. Right, so that's our centerpiece. We've got the first term of our linearization. So up next, we're going to need the x slope. So we should get a partial derivative with respect to x. So f partial x looks like something. Maybe if I zoom out a little bit. There we go. Now I've got my function at the top again. It'd probably be helpful to just write it down here, wouldn't it? F of xy is the square root of x plus x plus e to the 8y minus 3. All right. There we go. Now I've got some more space to work. So if I get an x partial of this thing, it is going to look like 1 over 2 times the square root of x plus e to the 8y minus 0. Derivative of 3 is going to be 0. Right, so remember square root is just that whole thing to the 1/2 power. And then I'm going to have to multiply by the derivative of the inside. But the derivative of the inside is 1 if I'm doing my derivative with respect to x. So just 1 over 2 square root x plus e to the 8y. Since we're right here, I'll also get our y partial, because I know I'm going to need both. So the y partial derivative, I'll get, again, 1 over 2 times the square root of x plus e to the 8y. And then the chain rule says I also need to multiply by the derivative of the inside. And the derivative of the inside of that square root is 8 e to the 8y. And then again, minus 0, because the derivative of 3 is still 0. Adding onto that, I'm going to need f partial x at 3, 0. And I'll need f partial y at 3, 0. All right, so I just take my point and plug it into both partial derivatives and get an x slope and a y slope. If I plug my point into the inside of that square root, we already saw that we're going to get the square root of 4, which is 2. So my x partial derivative should be 1 over 4, since that's 1 over 2 times 2. And my y partial derivative is going to be 2. since that's going to be 8 over 2 times 2. Simplifies to 2. So 1/4 and 2. I don't know why the division bar was so wide on that 1/4. All right. Now that we have all the pieces together, that's why it's all a little on the big side. Let me shrink this down a little. Wow, what am I bothering with that for? I can just make more space. All right. So I have these pieces together and I just need to organize them into my linearization. So L of X and Y is -1 plus my X slope times X minus 3 plus my Y slope times Y minus 0. And those are the 3 elements that make up my linearization, the 3 terms that make up the linearization. The last step was to evaluate this linearization at a point that's nearby. We were looking specifically for 3.3 or 3.3 and 0.01. So we're 0.3 away from our X value and we're 0.1 away from our Y value. So this thing will look like -1 plus 1/4 times 0.3 plus 2 times 0.01. And then from there, I could just plug all that into a calculator to figure out what my answer is. I'll leave that part as an exercise. Am I going to do that? No, let's just get a number. I can probably do this math. Right. Let's see. 0.3 over 4 is going to be 0.075. We're going to add 0.02 to that, so that's 0.097. And so if that's 0.097, does that make this negative 0.903? I think that's what it's equal to. Maybe someone in chat is going to correct me here in a second. Speaking of which, I have a question. Why is it 0.3 instead of 3.3? Referring specifically to this 0.3 right there. Oh, and probably the floating Zoom message might be cutting off the value I came up with. So yeah, why did that value come out to 0.3 instead of 3.3? So that guy is coming from X minus 3. My X value is 3.3, as noted. But right, yeah, so the X value itself is 3.3, but then I'm plugging it into X minus 3. So I get 3.3 minus 3, which is just 0.3. That's where it came from. And sort of the way that I think about this problem is that the X value I'm evaluating the linearization at is 0.3 away from my center. And then how did I know that X was 3.3 as the follow-up question to that? That is because it asked for it in the condition of the problem. It asked us to, approximate the function at 3.3 for X and 0.01 for Y. All right, and I'm hearing I got my number wrong. Negative 0.905 instead of 0.903. Does that make sense? I'm going to trust the chat. That probably works out for me. 9:05. Well, that's what I get for trying to do quick math on camera. Ah, well. All right, let's take this on to the next problem. So we're going to calculate a tangent plane. So what do we want to do? So we're going to start with what? We have two curves, R1 and R2. So each of these are parametric equations for curves. Curve being just a thin curved line that exists in 3 space. It only needs one parameter to describe the curve, so it's like a one-dimensional object, just that's bent and curved in 3 space. And I have two of them, R1 and R2. Both of them lie on some surface S and intersect at the point P. We want to find an equation of the tangent plane to the surface S at the point P. So a few different steps we'll run through here. Starting with the first step. If I know that these two things are equal to each other, or that I know, back that up. We know that these two curves intersect at the point P. So what I should do is use that point P to figure out what each of T and S are. And looking through the equations I've got for, or each of the components that I've got for T and S, the X, Y, and Z components, I notice that the Z component of each is particularly simple. I have negative T minus 1 and S plus 6. Those are both linear equations, and I need them to be equal to 2. So I will just solve for each of those numbers real quick. Negative T minus 1 is equal to 2. And on the other side, I'll have S plus 6 is equal to 2. Equal to 2. Yeah. There we go. Meaning that T is equal to negative 3 and S is equal to negative 4. I'm going to highlight those two pieces because I'll need them later on as we go. You can verify that that T value and S value are correct by plugging each of them in and seeing that you get negative 2 for 2 in both equations. But we only needed to solve a single component to figure out what S and T are. So that's helpful. We know what our parameter values are at the point of intersection, but now let's give some thought to what the actual question is asking us for. We want the equation of the tangent plane for the surface S at point P. All right, cool. So if we think about how do we get a tangent plane, well, we only need two things. We need a point to be tangent to. Fortunately, we already have that, negative 2, negative 4, 2. That's our point where we will be tangent. The other thing we need for a tangent plane is a normal vector. So the rest of the problem is going to be about finding that normal vector. Let's start by establishing a good idea or have a good thought about how to get that normal vector. So normal vector, N. Well, the probably easiest way to get a normal vector is to find two tangent vectors and get their cross product. Since I've got two curves that I know are on the surface and intersect at the point, I should be able to find a vector that's orthogonal to both of them by taking the cross products of their derivative vectors. So I want R1 prime cross R2 prime. Since R1 prime and R2 prime are both going to be tangent to the point P on the surface S. So if I get the cross product of those two vectors, it'll give me a normal vector. So that's the rest of the problem. That's the rest of our goal here. It's figuring out what that thing should be. So I am going to want derivative vectors. R1 prime is whatever the derivative of this thing is. Looks like negative 10t minus 4. And then 3 and negative 1 for our next two components. Since each of those were linear. Yeah, it's the same thing I got when I did it earlier. And we'll look at R2 prime. Make sure to include our vector hat over here. So make sure to include our vector hat over here. There we are. So I'll take a derivative of that other curve. And I'm looking at negative 6s 2, 1. So both of our derivative vectors still depend on t and s, but I can plug in the specific values that I got for t and s to figure out what the individual vectors ought to be. Yeah. Realized I made an omission in these vectors. These are still functions of s and t. So I should include that in there. It's still r1 of t. Okay, so now is when I'll use the part where I solved for t and s to figure out what the specific vectors are. I need r1 prime of negative 3, which is negative 30. Nope. Try again. That is positive 30 minus 4. Yeah. And 30 minus 4 is 26. 3, negative 1. And I need R2 prime of negative 4, which looks like positive 24, 2, 1. And now that I've got those two vectors, I'll go get their cross product. Our normal vector, n, is the cross product, I, j, k, of cross product of 26, 3, negative 1, and 24, 2, 1. So if I go get that cross product, what do we have? I'll have, come back, 3 minus negative 2. I'll have negative 24 minus 26. And I'll have 2 times 26 is 52 minus 24 times 3 is 72. Putting all that together, 3 plus 2 is 5. Negative 24 minus 26 is negative 50. And 52 minus 72 is negative 20. Cool, so that's a normal vector. If all we needed was the normal vector, we could stop there. But we need slightly more than that. We need to put this thing into the equation of a tangent plane. So this is 0 is equal to n dotted with the variable vector minus the position vector, that initial point. So it looks like 5 times x minus negative 2. Call that x plus 2 minus 50 times y minus -4 minus 20 times z minus 2. So to zoom back out for a second, it's probably been a while. We looked at the problem itself. Yeah, that point that we wanted to be tangent to was at -2, -4, 2. So that had to get plugged in right here. Question going on over in chat. Calculated the, nope, wrong one. Will the exam be similar to these review problems or more similar to the quiz problems? Probably a bit of both. I think that these questions all are at least fairly similar to the questions you'll see on the exam. Certainly, I picked them out because I thought that they contained at least something that you'd want to review before the exam. But the actual format will look similar to quiz questions. So it's kind of a mix of both. Content, pretty similar from this review. Format will be pretty similar to quiz questions. Hopefully that answers the question. Awesome. Looks like it did. At least it did live. If you're hearing this question in the video and it didn't answer the question, well, womp womp. Post about it on PS. I'll respond to it there. Ooh, this one. This is one of the ones I just added. Okay, another question. Sometimes I've noticed on web work which curve I put on top during the cross product matters. What is a good way of determining what goes on top, or does it not matter? It does not matter. It will change the answer, but it does not matter. So let's talk about that real quick. If you had done the opposite of what I did, you put the 24-2-1 on top and the 26-3 -1 on bottom, you'd get the same numbers as I got, at least if you did it right, 5, -50, or 5, 50, 20. Those numbers would all be the same, but all of your negative signs would be opposite from mine. So if you put them the other one on top of the 24 on top of the 26, you should have gotten -5, +50, +20. So basically, if you take the cross product in the opposite direction, you'll get the opposite pointing normal vector, or the opposite pointing orthogonal vector. And since the equation of a plane can work with either orientation for the normal vector, it does not change the solution. So either one's fine. The most common mistake we see with cross products is screwing up the y vector, or the y component of the vector, because you've got to you've got to get the sign of that cross just right. There are too many different ways to conceptualize the cross product that I don't want to get too into the weeds on the particular method. But again, most common mistake we see on cross products is just messing up the sign on the y component. Yeah, because if you want to think about it as 26 times 1 minus 24 times -1, you need to put a negative on that if you keep it the same orientation as the others. The way I tend to think about it is I always go left to right. Nope, that's not true at all. I always go to the right of the variable that I need to be doing the cross on. So when I'm getting the j cross product, I need to start to the right of j. When I'm getting the I component, I start to the right of I. When I need the K component, I start to the right of K. And to the right of K is 26. To the right of J is -1. I said I wasn't going to get into the weeds because there are too many ways to conceptualize cross products, but then I did anyway, because I'm just so good at talking. Yeah, so it's like the plus minus plus. If you think about it the other way, if you're conceptualizing cross product, one of the alternative ways, again, I could get, let's try, I'm going to bring it back and stay on task. If you have more questions on cross products, I'd strongly recommend watching my video on cross products. He said, just putting things off. Ooh, yeah, cool. Let's let's put me back to doing a math problem. Everyone will be happier if I do it that way. What's up next? We want to find an equation of the tangent plane to the parametric surface. X is 2u plus 5v, y is 3u squared, and z is 2u minus 2v. Cool. So let's do that. This one's very similar to the previous problem, where if we want that tangent plane, we're going to need a normal vector. We're going to get our normal vector by taking the cross product of two tangent vectors. And the way that we'll get our tangent vectors is by looking at a u partial derivative and a v partial derivative. So before we do that, let's just write down what our process is going to be. So similar to the last one, I'm looking for a normal vector. And I am going to want the cross product of a couple parallel vectors or a couple of tangent vectors, where those tangent vectors are u and v, r partial u and r partial v. That's going to be the plan. So let's go about getting that. Before we get the partial derivative vectors, why don't we solve for u and v? So we end up with 3 equations and 2 variables. So I've got 2u plus 5v equals 19. I've got 3u squared. My v look funny there. V, there we go. Yeah, still looks kind of funny. Oh well. 3u squared is equal to 12. And 2u minus 2v is equal to -2. Right, those are my three equations, and I need to solve them for u and v. So system of 3 equations, solve for my 2 variables. I'm going to solve the easiest ones, I think. Meaning probably I'm going to be solving the x and z components for u and v, and then I'll just verify that with the y component. Y has a squared variable in it, and I'd rather not deal with a plus or minus, so I'll solve x and z, which are both linear. So let's start with 2u equals 2v minus 2. I could divide both sides by 2 right now if I wanted, but it looks like it'll be easier to just substitute directly for 2u. This is 2v minus 2 plus 5v equals 19. So I'm taking this equation and substituting it in right there. It's my step 1, substituting the z component into the x component. Should solve that thing around for v. Looks like I've got 7 v's in total. 7 v's in total, and it's equal to 21. So I'll need to add 2 over to the other side. And if 7v is 21, v itself has got to be 3. Then, if v is 3, u is going to be 3 minus 2. Nope, 3 minus 1. Try again. There it is. Knew something didn't look right. Plug that guy in over here. And that makes u equal to 2. And then lastly, I could verify that 3 times 2 squared is indeed equal to 12. So it works in all 3. The trouble with having solved the u piece first is I would have gotten that u is plus or minus 2, and I'd have to figure out which one it is, because as it turns out, -2 for u doesn't end up giving us a valid solution, which is why I saved that one for last. It's oftentimes just cumbersome to deal with square variables. All right, I've got my u and my v. I think I had v in green, u in blue. So I'll mark them there and there. And I need to get partial derivatives for these two things. So it might be helpful to just write down what r is. R of u and v. Because it's just the vector x, y, z, where x, y, and z are all parameters, or all parameterized already. It's x, and then it's y, and then it's z. That's my curve. But I know what each of those are. X was 2u plus 5v. Scroll up just a little bit so I can see what they are. Y was 3u squared. And z was 2u minus 2v. Trying to be a little careful with my u's and v's so they don't look like each other. But yeah, if I just bring that back up here, I had my x, I had my y, I had my z. And I'm just substituting those into my r equation. And now I want to come through and get partial derivatives of that curve with respect to both u and v. So up first, let's get r partial u. And this is still of u and v potentially. Yeah, we'll add that in later. Yeah, it's still of u and v potentially. However, the two variables are completely separate, so we'll end up seeing that it only ends up being a derivative of one variable, if even one at all. So that thing's going to come out to 2, 6u, 2 is r partial u. If I do r partial v, again of u and v. Wait a minute, let's keep things consistent with how I did them last time. Put it below. But if I do a v partial, I'm going to get 5, 0, negative 2. Right, and then I'll plug in the values that I need. Oh, I forgot to put primes on those. R. Oh, no, I don't need the primes because I put the partial derivatives below. Man, what am I thinking? I don't know. I was thinking the old notation where I had R1 and R2, and those needed primes. But now the partials are the subscripts. There's a lot of notation in our class. I want R partial u of whatever point I decided this was, 3, 2. And that's going to make that thing 2, 12, 2. Nice thing about R partial v is that it's already constant. So it doesn't matter what point I plug in, I'm going to get that same piece. So let's go get a cross product. We need way more space to finish this problem. Not way more space, more like basically done. We just have a cross product left. N is the cross product of I, J, K, whatever two vectors I decided on, 2, 12, 2, 2, 12, 2, and 5, 0, negative 2. And that cross product I get is negative 24 minus 0. and then 10 minus -4, and then 0 minus 60, right? 5 times 12 is 60. I'll simplify that thing again and get -24, 14, and -60. Cool, so that's my normal vector. Now I just need to put this thing into the equation of a tangent plane. So did we have a point that was just given to us? We did. 19, 12, -2. So I'll get something like 0 equals -24 times x minus 19. I've already forgotten what the next number was. Plus 14 times y minus whatever its number was. I'll get that in a second. Minus 60 times z minus -2. That's z plus 2. Oop, close the parentheses at the end. And what was y's value again? 12, right? 12. Why did I remember only when I started scrolling? I don't know. All right, so then that's what I would think is good enough for the equation of a tangent plane. However, since this thing was a web work problem, it wasn't good enough. We had to get this specifically into the form of z equals something. So if I were to do that, I would copy and paste this line right here. Slide everything over to the right a little bit. I'm going to take my z component and bring it over to the right side. If I bring it over to the right, it becomes positive. Then I'll divide everything by 60. If I copy and paste this thing again, I'm being so lazy about this right now, but that's fine. Divide everything over here by 60. Grab the 60, move it over there. Then I also need to get z by itself, so I'll move the 2 over. Moving it over, it becomes negative. And hey, look, I've got z equals some equation. Hopefully that all worked out the way I saw it in my head. I think that translates to video well enough. At least I'm going to hope it does. I am going to check this answer real quick, unless someone that's here live happened to be doing that as I went. Zoom out. Look at the problem number again. Homework 12, problem 4. So someone's saying that all their signs were flipped for their normal vector. That's actually a good sign. That means you and I got the same answer if all 3 of your signs were flipped. Just means that you had a different vector on top than what I had. But since it doesn't matter which one goes on top, we come out to the same answer. We could multiply both of our equations by... We could multiply either of our equations by -1 to get the others. But I just said we were looking for... homework 12, problem 4, and then I opened up homework set 14 because I'm not very good with numbers. Yes. Looks like that was the correct answer. I love that for us. Cool. So yeah, just to reiterate, if you got 24, -14, positive 60, that would be an equally valid answer. And then, yeah, we'd have the same point. So I think all that should come out just fine. I did a very cursory glance to check that my answer was right. But I'm pretty sure it is. Again, I'm sure someone will let me know if I had it wrong. I'll post on Piazza if I had to correct something, if I don't catch it by the end of the video. All right, let's look at another problem. We've got a chain rule that we're going to do. So what are we after? We want, ooh, this thing ends up being a complete and total mess. Let's do the easy parts first, and then I might just like copy and paste the answers at the end. So, and in fact, since this thing is going to get nasty by the end, I'm going to focus just on getting dz ds, partial derivative of z with respect to s. The others are going to be relatively straightforward, so I'll calculate all of that, but in the end, I'll just do one of the ugly ones because it takes a whole bunch of copy and pasting to get there. So let's start by evaluating what it is that we are after. So we want the derivative of z with respect to s, dz ds. I'm going to use blue for s. So what that thing is going to look like is the derivative of z with respect to both of the variables it's a function of, which are x and y. So it'll be an x prime plus a y prime. But then each of x and y are functions of s, so I'm going to need to multiply an extra bit in for that part of the chain rule. So the x derivative is going to look like dz dx. So the derivative of z with respect to x, multiply that by the derivative of x with respect to s. That's the chain rule part. So x is a function of s, which means if I take the derivative of x, I need to put an x prime there and then multiply in x's derivative with respect to s. Y prime works pretty much the same way, except it's y instead of x. dz dy. So that's the partial derivative of z with respect to y. And then multiply that by the derivative of y with respect to s. Because again, y is a function of s, so every time I take the derivative of y, I need to multiply by y's derivative. The derivative of y isn't just one. Same thing earlier, whenever I take the derivative of x, I need to multiply by the derivative of x, since x's derivative is not simply 1. It is some other function of s. So let's put some of this stuff together. I want to get dz dx first. So I can look over at my function, which is this guy over here. I'll highlight it in that color. That's my z function. I need its x partial and I need its y partial. So if I'm going to do the x partial, I'm going to need the derivative of sine, which is cosine of negative 2x times cosine of 8y, and then multiply by the derivative of the inside of cosine, which is negative 2. So I've got a negative 2 cosine negative 2x times cosine 8y. For a dz dy, something pretty similar, I'll need sine of negative 2x times the derivative of cosine, which is negative sine, times 8y, and then multiply the derivative of 8y, which is 8. So negative 2 cosine cosine and negative 8 sine sine. Both of those are functions of x and y. Now I should go through and get the derivative of x and y with respect to s. So x is this guy right here, y is that guy over there, and I need both my derivatives with respect to s. So the derivative of x with respect to s is 2s. S squared's derivative is 2s, t squared's derivative is 0. On to the next part, 3 minus 2st. That derivative is negative 2t. All right, and now let's put the structure of this thing together. If I want z partial s, which is the thing I'm after, construct this whole thing out of something. It is an x partial, which I guess I don't want to put that too far off screen. That x partial was negative 2 cosine of negative 2x cosine of 8y multiply in the chain rule part, which is 2s. 2s. Plus. And if you've struggled on this WebWork problem for hours at a time, you are probably ready to point something out to me. Don't worry, I'll catch that in a second. But I want to add into this thing a little bit of color because I wanted that in purple. That's my x partial. I need to add in my y partial, which it's going to be off screen, but we'll deal with that at the end. Negative 8 sine negative 2x cosine 8y. Close the y partial, and again, multiply in the s partial, which was negative 2t. Cool, and that is an answer. Of course, it doesn't quite yet get to be the correct answer because we need our final answer to be in terms of only s and t. So out of a sense of laziness, because this gets long and messy, I'm just going to copy and paste in what that answer ought to be. Burp. Ta-da! Well, as soon as it loads. Yeah, there's our answer. So if I kind of mark some things off here, this section right here was our x derivative. And then this section right here was our y derivative. And all I did was replace x and y with their expressions for s and t. It's getting a little cluttered, so I'm going to take those back out. But yeah, that's our z partial s. If I did the partial t, it would all look very similar to this. The only difference is that those blue bracket sets would be replaced with green bracket sets for the t partial derivatives. And then let's just, for anybody that's just looking at the written notes, I'll circle the answer I was after. Because yeah, that went in for z partial s. And I'm going to just leave it on that. Just this half of the problem. And mercifully move on. Aha. And then I added another one. So within the chain rule, we've got a couple of different types of problems we looked at. One was a chain rule that involved multiple stacking variable systems, or multiple stacking parameter systems. The other type of derivative we looked at in this section was an implicit derivative with multiple variables. And that's this half. So let's go take a look. What do we want to do? So consider the equation here. Find z partial x and z partial y. So what I want to do is just take that whole equation and get an x derivative and a y derivative, keeping in mind that anytime I see z, I have to treat it like it's a function of both variables. So if I'm going to do an x partial, what am I going to get? I'm going to get 5y z prime. Because again, I have to treat z like it's a function of x, plus, this will just be e to the y, because derivative of x is 1. It is equal to, on the other side, negative 6z times z prime minus 7 cosine x. And then I should just solve this thing for z prime, which means I'm going to gather up all my z primes on one side. 5y z prime plus 6z z prime. And then that's equal to negative e to the y minus 7 cosine x. Factor a z prime out and divide the rest over to the other side. So z prime is negative e to the y minus 7 cosine x over 5y plus 6z. And then I'll do that same thing for the y partial. So I just slide that over to the right for a second, pull the thing back on screen, and try again. Next up, I'll have 5z plus 5y z prime plus x e to the y. And that's equal to negative 6. Did that in yellow last time? Negative 6z z prime plus 0. All right, because that 7 sine x doesn't depend on y. And again, just solve this thing for z prime. Gathering all that stuff on one side. 5y z prime plus 6z z prime is equal to negative 5z minus x e to the y. Factor out and divide by everything that isn't z prime to get negative 5z minus x e to the y divided by 5y plus 6z. And then the yellow one goes here, the purple one goes there. Okay. All right. On to problem 14. Yeah, looks like we're good to go. All right, problem 14. What's it going to ask for? We're into directional derivatives and gradients. It wants us to find the maximum rate of change of some function and also the direction in which it occurs, keeping in mind that that direction must be a unit vector. So, a good concept to know for the exam. The maximum rate of change of some function always points in the direction of its gradient. So if we want the maximum rate of change of some function at a given point, it just means take the gradient. So that's step number 1, is get gradient f, grad f, grad f. And it's equal to f partial x for the x component and f partial y for the y component. So if I just take the derivative of that thing right on down the line, I am going to get negative e to the negative 3xy plus 3y x e to the negative 3xy. And it's plus 3 because there's a double negative happening. Then if I go get the y derivative, that one's a little bit nicer. It'll just be positive 3x squared e to the negative 3xy. So that's our gradient. Up next, now that I have the gradient itself, the function, I just need to plug 3,0 into it and see what shakes out. This thing looks like, if I plug in 3,0, I'm going to get negative e to the 0, which is just negative 1, plus 3 times 0 times other stuff. I don't care anymore. As soon as I multiply by 0, no, that thing's just 0. And on the right, 3x squared, that's 3 times 9, which is 27, times e to the 0, which is 1. So my gradient vector is negative 127. The last element I need here is the magnitude of that gradient. Which is no longer a vector. It is instead a square root of 1 plus 27 squared. As we all know, 27 squared is 729. So 729 plus 1 is 730. We'll just leave that thing as square root 730. So now we have all the pieces in play to answer the original questions. The maximum rate of change is the magnitude of that gradient. So our maximum rate of change should be a scalar value, not a vector. And that maximum rate is just square root 730. Think of maximum rate of change as like your max speed. Your speed's not a vector, it's just a number. Then the direction that that thing occurs in, being the unit vector, is the gradient vector divided by its magnitude. Negative 127 divided by root 730. So those are the individual pieces to finding the maximum rate of change. We'll break it down into a scalar component, like a speed and a direction. Oh, no. All right, then time for everybody's favorite part of this exam. finding absolute maximum and minimum values on some function that satisfies some boundary condition. And since I know what problems I have lying ahead, I'm going to solve this one without Lagrange multipliers. And then the next problem, I will use Lagrange multipliers. Now that we've learned Lagrange multipliers, we could use them in both problems. Though this one was from the set where we weren't using them, so I'll also work without them. But it could work either way. So let's talk about the steps involved in finding maximum and minimum values. Step number 1 is finding all the critical points. Find all critical points. We're going to do this on the 2-dimensional region. So these find all critical points, this find all critical points step is a 2-dimensional step. Step number 2 is going to be to find all critical points on the boundary. Find all critical points on the boundary. Once we break it down to a boundary, this is a 1-dimensional problem, which means it's going to look very similar to a Calc 1 problem. The boundary also includes its boundary points, if we have those, including boundary points. This is also the step where we could use Lagrange multipliers. Could use Lagrange multipliers. Since Lagrange multipliers are particularly good at finding values along the boundary, but we need a specific boundary to be on. This thing, we have an inequality for our, like, sort of our boundary set. So we'd have to break it down into an interior and a Lagrange set. That's why we'll do it the old way. But again, we could use the Lagrange multipliers for step number 2. And then finally, the third step, that's the easy step. We just check all our critical values. Check all critical values. That's the step where we just take all the points that we found, plug them back into the function. Biggest one's the maximum, smallest one's the minimum. Once we get there, we're done. So those are our 3 steps. Tends to be step number 2 is generally the nastiest one. So with that in mind, start with step number 1. We are going to need a couple of things. We need f partial x and we need f partial y. F partial x looks like just 2x. And I want that partial derivative to be equal to 0. I'll also look at f partial y, which is slightly more involved. Looks like 8y minus 16. I can read 8y minus 16. I also want that equal to 0. It's going to give me 2 solutions. Well, 2 solutions. I have 2 equations. Each one has 1 solution. X equals 0 and y equals 2. Meaning that I only come up with 1 critical point, 0, 2. That's the only critical point we have. If we had a more complex system, we might need to substitute the x partial into the y partial and then figure out something from there. But these ones were pretty straightforward. So it's just 1 solution from each of the two partial derivatives. Means we've only got the one critical point. So on to step number 2. Finding all of the critical points on the boundary. So if I come back up to what our boundary was, I already found the one critical point that's where x squared plus y squared is less than 36. Now I want to look at the boundary where x squared plus y squared is equal to 36. X squared plus y squared is equal to 36. And again, that bit is our boundary. So what I'm going to do is substitute one equation into the other. Probably the easiest way to do that is recognize that f, which was x squared plus 4y squared minus 16 minus 2, that was my function. I'm going to split up my 4y squared into 1y squared plus 3y squared. That's the step I'm going to notice and deal with first. Because if I do that, I've got this x squared plus y squared right here, which is just 36. And then plus 3y squared minus 16y minus 2. We hope if I transposed the problem correctly. Yep, it was even already in chat. Thanks. Yeah, I noticed as soon as I had to start doing math again, I'm like, there's no way that I had two constants. That wouldn't have made sense. I would have dealt with that already. All right, so now this is my equation on the boundary. And the nice thing about the boundary function, and you'll know that you've got your boundary function at least somewhat correct, if it's only a function of a single variable, a function of only a single variable. There it is. So my new boundary function is just g of y, or I could just call it f of y, but we usually relabel it when it's on the boundary, which means that I actually should have relabeled it right up here. G of y is that thing, because then I can get a derivative of that. And the derivative of that mess looks like 6y minus 16. And now I want to set this thing equal to 0, which is going to give me a y value of 16 over 6, or I could simplify that to 8 over 3. So I then want to take that solution and plug it back into what I know for x. X squared is 36 minus y squared. 36 minus 8 over 3 squared. Just going to grab that and plug it in right here. Grab that, plug it in right there. And that means that x is equal to plus or minus the square root of 36 minus 8/3 squared. And that thing is approximately plus or minus 5.3784. Went to a calculator ahead of time. Don't want to give away this thing just yet, because what I will do is bring in a sketch of what this thing looks like. Take me back here. Yeah, that's fine. create some more space. Paste in this guy. All right. Another diagram that I wanted to bring in, but that I had left over in my other notes. We'll sort back here. Hey, it loaded. Perfect. Okay, so if I just look at my region real quick and kind of identify where all of my critical points are, I have the blue one that's at the center. That's the critical point and the interior that I found in step one. I also have the two critical points that I found on the boundary. I was using green for the boundary, so I labeled them in green. Those are right there, those two green points. And then also, because my boundary was a function on just y, I need to look at the limits of y, the upper bound and the lower bound for y. So y's upper bound would have been positive 6, because this thing is a circle with a radius of 6, and a lower bound of negative 6, which gives me my two boundary points of 6 and negative 6. Or well, 0, 6 and 0, negative 6. Let's be a bit clearer about that. So with these now 5 points all together, I just need to plug each of them in to find my maximum and minimum. And I also did that step ahead of time because it seemed easier that way. Why don't I actually probably label those guys in green just to keep things consistent. So after plugging them all in, I found that interior critical point I found was the minimum value at negative 18. And one of my boundary points, 0, negative 6, was our maximum value at 238. In the end, it's just simply plug them back into the original function. Biggest one's the maximum, smallest one is the minimum. And we should also look at Lagrange multipliers, because we'll probably do one problem like that on the exam itself. So with Lagrange multipliers, remember the thing that we're trying to do is set two gradient vectors parallel to each other. So I'm going to need the gradient of both my function and its constraint. And it's also important that our constraint equation just be equal to some constant number. So that's an element of the Lagrange multiplier constraint that's important. It must be simply equal to a constant rather than an inequality like less than or equal to a constant like we had in the previous problem. We can still use Lagrange multipliers in those kinds of problems, but we need to separate them out into a boundary problem and an interior problem. Which maybe we'll look at doing the previous problem as a Lagrange multiplier later on, if there's still some interest by the time we get to the end of this video. So we're probably going a little over on my estimated time, but I digress. I want gradients of these two functions. It looks like gradient of f is going to be 3, 4. That one's not too bad. And then the gradient of g is 2x, 2y. And we want to, well, it says express x and y as a function of L such that gradient f equals L times gradient g. I'll probably just skip over that step and get to the next part because sometimes it's more effort than it's worth. But if I were to set up the equations that this thing gives me, if I've got, grad f equals, we usually call it lambda, but oftentimes in WebWork it's L. There's no difference between the two. Just one is easier to type. So I want grad f equals lambda times grad g. I get the following. 3, 4 is equal to lambda times 2x 2y. Yeah. And this will generate 3 equations for me to solve a system of. So I will get 3 equals 2 lambda y, 3 equals 2 lambda x, excuse me. I will get 4 equals 2 lambda y. I'll say it right this time, 2 lambda y. And finally, my boundary equation comes back, x squared plus y squared equals 1. I need to solve this system of 3 equations for my 3 variables. So I should probably get something like x equals 3 over 2 lambda. I'll get something like y equals 4 over 2 lambda. I'll just call that 2 over lambda. And then I can substitute both of those into the boundary equation. 3 over 2 lambda squared plus 2 over lambda squared is equal to 1. If I kind of like bring all of my parts together, hands getting tired. It's not that hard. And then also this equation. Let's try again. Also this equation all come together to give me a single equation with only one variable, only one parameter. So I can solve that thing for lambda. And what is this thing going to look like? I should have left it as 4 over 2 lambda. Would have made my life a little easier. Well. So this thing looks like 9. Let's try again. 9 over 4 lambda squared. 4 lambda squared. Plus this thing on the right looks like 16 over 4 lambda squared. That's equal to 1. So I end up with 25. Why am I bothering with it that way? This is 25 over 4 equals lambda squared. Which means that plus or minus 5 over 2 is lambda. So positive 2.5 and negative 2.5. Bring it over here, 2.5 or negative 2.5. And so with those 2 lambda values, I can use them to get an x and a y point. So I get either x equals 3 over 5, y equals 4 over 5. I'm just going to go ahead and change that back. 4 over 2 lambda. 4 over 2 lambda. Just made my fractions a little bit nicer. It was easier not to simplify. So x is 3/5 and y is 4/5. Or I get x is negative 3/5 and y is negative 4/5. So those are my 2 points. And now I just need to plug them both in. I could also, let's call this 0.6, 0.8, and negative 0.6, negative 0.8. just because those decimals come out pretty nice. So let's find the maximum value and minimum value. It just means plugging them both in. F of 3 over 5, 4 over 5 is, what was our function? 3x plus 4y. So that'll be 9 over 5 plus 16 over 5, which is positive 5, 25 over 5. And f of negative 3 over 5, negative 4 over 5, which is negative 9 over 5, minus 16 over 5, which is negative 5. So our maximum value is 5, and our minimum value is negative 5. And that was a Lagrange multiplier. So I'll take that into the next problem. Don't have too many more of these left, I don't think. But I've been known to surprise myself before. Something out of vector fields. Oh yeah, we definitely have some more stuff. Okay, so write down the given line integral in terms of t with the added equation here that work is equal to a line integral of some kind. So this, I know, came up in at least a couple of the WebWork problems we have, but just something that I think will be important to know for the exam is that if we're asking for the work done by some particular vector field, we can calculate it using this line integral problem, where we're integrating the force field, which is F, dotted with the position derivative vector. That creates a work integral. So if you've taken a physics class, which, I mean, by the time you've gotten to Calc 3, you've probably seen at least a little physics. There's the algebra function, or the algebra formula for work, which is just force times distance. This is a more sophisticated work formula for a force field that is not constant, integrating through a variable force field. And that's our equation. So I wrote it down here because, again, thought it might be helpful to know for that exam. I also maybe said that the exam was tomorrow a moment ago. That's not right. Unless you're watching this video on Wednesday, and then it is tomorrow. But I'm recording this on Monday. Tomorrow is definitely not the exam. Tomorrow is Tuesday. I'm tie. All right, focus. Back on task. Write down the given line integral in terms of t, given a bunch of stuff. So what do we want to do? We want to integrate y ds, given that the curve is x is equal to negative t squared, y is equal to negative t. So if I were to just write that thing down, this thing really looks like a parabola. It's y equals negative x, or try again. It's a parabola. It is x equals negative y squared. And that thing looks like the vector negative t squared t. That's our curve as a vector function. Vector valued function, that thing right there. Specifically with t being between 0 and 1. So we might as well get one of the easy parts out of the way first. If t is between 0 and 1, that means that a and b are 0 and 1. That's going to be particularly nice for us. But for the rest of it, we need y times ds. Y is easy. It's just t. So I've got to figure out what my integrating factor ds is equal to. And since I'm not working with a vector valued function, right, my function is just f equals y, it's a scalar function, I need to use the formula for ds that says it is the square root of the x partial derivative squared plus the y partial derivative squared. So that x partial is negative 2t, negative 2t squared plus the y partial is just 1 squared. And so that thing is the square root of 4t squared plus 1. So that also goes in the integrand box over here, 4t squared plus 1. Oh, and I suppose I should also have included the dt in here because I'm being proper about it all. dt. So we've successfully changed our ds, which is a small infinitesimal change along the curve, to an infinitesimal change in our parameter t, which is what we needed in order to integrate this thing. So with all that set up, we just have to go integrate the thing, and it's not as bad as it looks. There's a pretty nice u substitution. U is just the thing on the inside of the square root. It's 4t squared plus 1. That means that du is equal to 8t dt. So I am actually going to integrate the square root of u times du I already have the t that's in there, but I'm missing the factor of 8. So I'm just going to multiply in a 1 over 8 on the outside to get that u substitution to work out nice. That's the only part I was missing, was just a constant. That has a very nice integral. I still have this 1 over 8. But if I'm integrating u to the 1/2, all I need is the power rule. It is u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. Then I'm going to just substitute back in for t. 1 over 8 times 2/3 is 1 over 12. 1 over 12 times 4t squared plus 1 to the 3/2 power. And then we need to evaluate that thing between 0 and 1. This thing is going to look like 1/12 times, if I plug in 1, I'll get 4 plus 1 to the 3/2. So 5 to the 3/2 minus plugging in 0. 0 plus 1 is 1 to the 3/2, which is still 1. So 5 to the 3/2 minus 1. All of that times 1/12. All right, on to our next problem. Also from homework set 17, evaluating or identifying vector fields. And hang on just a second. I think that was my doorbell. All right, identifying vector fields based on some vector function. So we've got 4 options over here, and we want to match them up with the vectors on the left. So if I were to start by identifying what each of these look like, why don't I start with one of the easier ones? I want to get number 4 first. I think that one's going to be pretty straightforward. Things I expect to see. That vector field has no dependence on x. So as I look from left to right, I expect all of my vectors to stay the same. Shifting shifting the graph left and right should not change the vector field at all. Because again, it's not dependent on x at all. If I were to say just look at the x-axis, which is the line y equals 0, I would expect to see a whole bunch of vectors that are 0, 2, meaning that they just point straight up. And what's another good thing to look at? If I were to look up and down the x-axis with x equals 0, I'd expect to see things that point more up and right as I go up the x-axis because y is increasing. And as I move down the x-axis, I'd expect to see things that point more left and down. So with all that together, I'm looking at option C for this one. C, I'll put it right there. And again, sort of the element that I thought was most indicative of this problem is right along here, right along that x-axis. I'm seeing all of those vectors that just point straight up. Each of those vectors is 0, 2, because y is 0 along all those points. What's another good one to look at? How about number 2? Just x negative y. I know that xy is going to look like a whole bunch of points that all point radially outward from the origin. But with this one, where I've got x negative y, it'll have a kind of similar style of pattern that shows up, but not exactly that. So what I should think to find instead here is that along the x-axis, I'm going to see all of my vectors be pointing outward. Right? If I'm going along the x-axis, if y is 0, I just have the vector x 0, that should point outward from the origin. But if I look along the y-axis, up and down, when x is 0, I should have vectors that all point directly into the origin, because they're just going to point opposite of the y value that they're on. So I am seeing all of these vectors here that point out, and these vectors here that point in, which means I think that D is a good option for number 2. And the vector fields, or the vectors around the axes, all kind of just morph from one into the other. After that, the trig function kind of makes me not want to solve that one. So I'm maybe just not going to do that one right away, and instead look at the first one, y and x minus y. What's the color? How about blue? I'll look at this one. Specifically, I'm going to look at that y value where I've got x minus y for whatever the y value is. Meaning, if I were to look along the line y equals x, I should see some kind of a pattern along that line. I'm expecting to see y equals x show up as something interesting in the problem. Since everywhere along the line y equals x, the y value of my vector is 0. So if I were to just come sketch that in along this graph right here, I'm looking at this line and hoping to see something interesting. And I kind of do. Like I can see, like as a whole, that line seems to be important for this vector field. But also at each point along that blue line I sketched in, I have purely horizontal vectors. It looks like I missed just a little bit with my accuracy on that. So let me just adjust it to be like right here. Yeah, that looks better. So I think that option A is a good one for number one. Because again, I see that y equals x line show up inside my vector field. And then, I mean, process of elimination then tells me the last one. This one's got to be B. But things I'd expect to see from this vector, since the y value only depends upon x, as I move further as I go to the right, I should see my vectors pointing up. And as I move to the left, I should see my vectors pointing down. Generally speaking, with the x value being some cosine number, that's going to kind of cycle through some stuff. So I'd expect to see some kind of vaguely circular pattern show up somewhere, since sine and cosine both generate circle patterns. And there's like a few sort of circly shapes that I can see inside that vector field. But really, when I'm identifying that, I'm probably looking at the y value. As I move to the right, I expect all of my vectors to be pointing up. As I move to the left, I expect all my vectors to be pointing down. The further right I go, the more up they point. The further left I go, the more down they point. So that's my thought pattern for identifying those four vector fields. Mm-hmm. All right, and now we're into line integrals. And I think especially we'll be looking at the fundamental theorem of line integrals. Oh no, that's not till homework 19. Either way, we're going to look at line integrals for the next couple problems. So let's give that a shot. For this first one, we want to integrate this function along an arc of the circle, x squared plus y squared equals 16. We're going to be going specifically from 4, 0 to 0, 4. So if I were to just plop some coordinate axes on here real quick. 4, 0 is along the x-axis. So something about like right here. And 0, 4 is on the y-axis. So maybe something like up there. And we're going to be going counterclockwise from one point to the other. Counterclockwise being this direction. It's easier for me to draw arcs clockwise, though, apparently. So we are starting here. And we are ending up here. And we need to parameterize that curve. So since I'm looking to parameterize a circle, polar coordinates are going to be the best way to parameterize that. So I'm going to leave that note over here. Think polar coordinates. Coordinates has an E in there. There we go. And the polar coordinate equations we have are x equals r cosine theta and y equals r sine theta. That's our base idea for our parameterization. So with that in mind, I think our best and easiest parameterization is going to be 4 cosine t, 4 sine t. Where we'll use t to represent theta and we're on a circle with a radius of 4. We're staying on the edge of that circle, so r is at a constant value of 4. Then I need to pick my starting and end values for t. We're going to start at an angle of 0 radians, and we're going to end at an angle of pi over 2 radians. Right, we're starting on the x-axis, that's an angle of 0 radians, ending on the y-axis, which is an angle of pi over 2 radians. So we'll integrate from 0 to pi over 2. Or rather, our curve goes from 0 to pi over 2, which also means we'll be integrating from 0 to pi over 2, since that was our goal, just to calculate some line integral. So next up, I need to substitute in my parameterization, which means I should come up with dx and dy. Dx is -4 sine t, while dy is 4 cosine t. Oh, let's be proper about this. I tend to forget that a lot. -4 sine t dt and 4 cosine t dt. Right. Put that where I don't have the pictures on the right covering up the work. And then let's substitute everything in. I need 6x squared dx. So that'll look like 6 times 4 cosine t squared times -4 sine t. Then I need to add to that 2y squared. So 2 times 4 sine squared t. And then multiply that by 4 cosine t. That's my dx. That's my dy. And then this should go right inside that box if I'm evaluating the web work problem. Mm-hmm. Why sine squared? Because I wrote it in twice. Good catch. I was just thinking ahead and wrote down too fast. Yeah, it should have just been 4 sine of t and then that thing squared. Yep. So then after that, what do we need to do? We need to actually go and evaluate the integral in the end. So let's go write all that down. I am looking to integrate this function from 0 to pi over 2. And my function looks like 6 times that whole thing. I'm going to be lazy and copy and paste. Give me a copy, give me a paste. dt. All right, the nice thing about the way all this was set up is that we already have our x and dx set up quite nicely. So for a u substitution, it's a pretty nice integration. If I'm basically integrating 6x squared dx, which will be 6x cubed over 3. So this looks like 6 over 3 times 4 cosine t cubed. Plus, added onto that, 2/3 times 4 sine of t cubed. Might have said 4/3 when I meant 2/3. It is 2/3. I'm still integrating from 0 to pi over 2. And I just need to plug those two things into sine and cosine. Nice thing about all that is that they are both nice values to plug in to sine and cosine. Cosine of pi over 2 is 0. And sine of pi over 2 is 1. Should have been cubed. Minus, subtracting from that, 6 over 3. Wait a second. That's not 1, that's 4. Sine of pi over 2 is 1. But then it's sine times 4. Then I've got 6/3 times 4 cubed. Since cosine of 0 is 1. So 4 cosine 0 is 4. Plus 2/3 times 0 cubed. Since sine of 0 is 0. Make myself a little bit more space. And my pen died. Hang on 1 second. All right, and now that we're back, we just need to add all this stuff up. This is going to look like 2/3 times 4 cubed minus 6/3 times 4 cubed. So this is negative 4/3 times 4 cubed. Which is probably where I'll introduce the idea that 4 cubed is 64. So 4 times 64, that's a power of 2. Must be 256 over 3. Yeah, still working. Awesome. Cool. So then that was our answer to the line integral. All right, and last problem. At least last problem that we'll work out. I've got a couple more that I'll just talk about briefly. We've got a fundamental theorem of line integrals to look at. So we want to find some initial scalar function f such that the gradient of f looks like the vector function we see here. So in order to find that function, I'll want to integrate each piece. So if I do that, I'll want to integrate negative 2yz e to the xz dx. I'll also want to integrate negative 2, let's try again, negative 2 e to the xz dy. And finally, integrate negative 2 xy e to the xz dz. And look at the result to each of those. In that first one, if I integrate that with respect to x, I'm going to get negative 2y e to the xz plus some constant value, plus c. If I integrate the y function, I get negative 2y e to the xz plus c. And if I integrate the z function, I will again get negative 2y e to the xz plus c. So because I keep getting this same function, negative 2y e to the xe, negative 2y e to the xe, negative 2y e to the xz, that must be the original function, the original scalar function f that had the gradient that went to each of those three components. If there were any additional pieces that were in here, I'd have to include them in the original function as well. But in this case, I only get the same expression that keeps showing back up. Negative 2y e to the xz. So that would be my original function. And I can verify that by taking each derivative again and seeing that I get the gradient that I started with. So since that worked out, I could also have done a test for a conservative vector field to verify that this thing works out to be a conservative function, so I can find f. This problem was just supposing we can already do that. I'm going to show off a better example later on of how to identify a conservative vector field. For now, I'm just going to say that, hey, like we have this function, so it must work. So we were asked to integrate that gradient vector field, which can be parameterized by r of t between t equals 0 and t equals 1. And instead of doing that, because that looks kind of terrifying, having to substitute all that stuff in for t, I'm going to instead use the fundamental theorem of line integrals to evaluate this thing in a much easier way. So I know that I'm looking between t equals 0 and t equals 1. So I'm going to look at r of 0 and call that point A. And then I'll also look at r of 1 and I'll call it point B. But starting with 0, I'm plugging that into my r function. So 0 squared plus 2, 0 squared minus 5, and 0 minus 0. That's 2, 5, 0. For my other point, I'm going to call it B, r of 1. Plug 1 in for t, and I'm looking at 3, negative 4, 0 again. And I just realized there's a mistake in the first one. That should have been 2, negative 5, 0. Working a little too fast, I guess. All right, so then the fundamental theorem of line integrals, which is basically the fundamental theorem of calculus, but for line integrals, says that if I'm integrating a function between a and b, then it's just equal to the integrated function evaluated at b minus the integrated function evaluated at a. So we're really just looking at f of b minus f of a, is what I'm trying to say. F of b minus f of a. So that's our fundamental theorem of calculus. That should look like f of 2, negative 5, 0 minus f of 3, negative 4, 0. Which will look like negative 2 times... I wrote these down backwards, didn't I? Yep. Try that again. I wanted f of b minus f of a, right? Final minus initial. So 3, negative 4, 0, and 2, negative 5, 0. There we go. That's the correct order. F of b minus f of a. So that'll be negative 2 times negative 4 times e to the 0, which is 1. Again, that was negative 2 times negative 4, e to the 0, which is 1, minus negative 2. So plus 2 times negative 5, e to the 0, which in the end is just negative 2. I was kind of jumping over a bunch of steps. Let me show that step out a little bit better. This is -2 times -4 times e to the xz. So 3 times 0 plus 2 times -5 times e to the 2 times 0. That's the work that went into that step. Sure that there's at least a couple of you guys out there that were wondering where I was pulling those numbers from. I was getting them from that function f that we had established up here. F is -2y e to the x z. Okay, so at least I think, yeah, that got me to the end of all the problems that I wanted to do collectively. So just like the last review, I've got a few more problems that I've already done up that I just wanted to talk about a couple of elements on. Maybe some stuff that it's more conceptual, involving, maybe more of a true-false kind of a question. So when we were asked to find the absolute maximum minimum of some function here on the triangular region between the 3 points given, I thought it was helpful to sketch out that region and then talk about all of the points that we find. So here, this red triangle is the region that we're looking at. And if you follow the steps outlined in one of the previous problems that we did, you'll find, I think this is 7 points altogether that we'll need to test. There's one critical point on the interior. That's the one highlighted in green or marked in green. There are the 3 boundary points that all need to be checked: 8, 0, 0, 7, and 0, -7. Those are the ones that are highlighted. And then each of the boundaries will also have a critical point on those edges. So I'll parameterize each edge with the equations given: y equals 7 minus 7/8 x, y equals 7/8 x minus 7, and x equals 0. Those are my 3 boundary equations. And then each of those will have a boundary critical point to evaluate as well. So all 7 of those. And one of the ways that we might have to evaluate that function is just by substituting in for y. So along the purple line, the one that's down at the bottom, I'll just substitute what I know for y, which is 7/8 times x minus 7, and plug it in for y in the original function. All right. I said earlier that I'd save checking for a conservative vector field for later, and here's what I meant. In a 2-variable problem, or a 2-dimensional function, a 2-variable function, there it is. If I need to check to see if I have a conservative vector field, I just need to take each of my 2 components, I've labeled them P and Q, do the opposite derivative of their position and check to see if they're equal. So some of the thought process that goes behind why this check for a conservative vector field works is that I'm assuming my vector field is the gradient of some function, which means the x component is already an x partial derivative and the y component is already a y partial derivative. I'm assuming it came from some function that I don't know yet, but I'm assuming it came from some function where the x component was the x derivative, y component is the y derivative. So if I want to check to see if this thing is conservative, meaning check to see if there really is some function it could have come from, I want to compare the second order xy partial derivative to the second order yx partial derivative, right? So I'm going to take the x and y partial derivatives of both pieces. Since I'm assuming the x component already had its x partial derivative, I'm going to do the y partial derivative to add that in. I'm assuming the y component already had the y partial derivative, so I'm going to do the x partial on top of it. That way I've done x and y to both left and right. And as long as it's a conservative vector field, I should get the same thing both times. And it's not a conservative vector field if I don't get the same thing both times. It means my original assumption that my p, my x component, was already an x partial, and that q, which is the y component, was already a y partial, must have been wrong. So that's how we check to see if these things are conservative in 2-space, and in a 3-variable problem, we just have a lot of stuff to check. So we need to check to see that each of the second order partials are equal to each other, which ends up with the green highlighted equation that's up there, which I think is a little bit daunting to look at first. So I'm going to simplify it over here on the left. What each of those lines is really saying is that the xy partial is equal to the yx partial. The xz partial should be equal to the zx partial, and the yz partial should be equal to the zy partial. Again, I'm already assuming that each of p, q, and r are a partial derivative of some kind already, right? Over here on the right, I'm assuming that it's already partial x, partial y, partial z in that order. So I'm just going to complete another partial derivative on each spot and check to see if they work out. So if I'm looking at my original gradient vector, which is 2y, 2x, xy, I'm assuming that fx is 2y, fy is 2x, and that fz is xyz. So I'm just going to add in the extra partial derivative and check to see if this thing is conservative. And I find that this particular example is not. Since if I do, all right, I'll start with the x partial and I'll do the y and z partials to it, and then compare to the correct place. And I get that they end up not working out with each other. I get that, the xz partial derivative is 0, but the zx partial derivative is yz. So that didn't work out for us. I also get that the yz partial derivative is 0, but the zy partial is xz. Probably maybe be pointing some stuff out. The xz partial and the zy partial, those are the two parts I'm looking at. One was 0, the other is xz. They aren't equal to each other. I also looked at the xz partial and the zx partial and saw that those weren't equal either. So when I'm identifying which pieces didn't work out, it was the xz partial and the yz partial. So I just picked the second two options. If I looked at xy and yx, I got that both of them were 2. Another problem that I just wanted to talk about a little bit is the second derivative test for local maximums or local minimums. That's where we look at the determinant of all those second order partial derivatives. Second derivative test is listed right here. Decent thing to remember when going into the exam. Remember that in order to have either a maximum or a minimum, that determinant must be positive. And then we can look at a single second derivative to decide if it's a local minimum or a local maximum. Concave up means we have a minimum, and concave down means we have a maximum. But we need the determinant to be positive first. If D is negative, we don't have a maximum or a minimum at that point. Some other stuff with line integrals. We had a density function for this problem that I thought was interesting to look at. Mostly I wanted to point out that if we wanted to find the total number of mosquitoes that Harry Potter gets splattered uh, on his Quidditch vest or something. Da, 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 da. Oh, right, his nice clean uniform. That's what it was. Uh, Figuring out how many mosquitoes end up on Harry just means integrating a density function. Just wanted to set that up right here. And again, didn't want to get too lost in the weeds on that. All right, and that's the end of the problems that I'd planned to go over. If you're watching this video on Wednesday night, good luck on the exam in the morning. If it's not Wednesday night right now, remember that the exam is on Thursday at 7 o'clock. You'll just take it on D2L like you've taken all the other assignments. And unless I think of something else the next 5 minutes to chime back in with, this is where I'll leave you watching the video. So good luck. And yeah, that's me.